Hi, it's Steve, and in today's project, I want to use my Atari 2600 to compute the Fibonacci sequence. However, I am not going to use the de facto controllers to do that. These things are somewhat cumbersome to use, and they require this little orphan Annie secret circle decoder sheet. Instead, I'm going to use a proper keyboard with the help of what's in this magic black box. Let's get this gear transformed. Now that we're ready to go, let's first maximize our screen real estate and then start entering the program. Print Fibonacci of X. Initial conditions. Finally, go to 3. And that should do it. Let's run the program. And there we go. Those are the Fibonacci numbers being generated by an Atari 2600 up until the overflow happens and they start wrapping around. But the nice thing about this is I can slow the program down so it executes one statement or one instruction at a time. And I can also speed it up so it executes really fast. I can also halt the program, and let's do this and step through it one statement at a time so you can see exactly what the interpreter is doing. Pretty neat, huh? Of course, this is nothing new. You could do all of this stuff with basic programming. It's just now that you can do it with a modern keyboard and not have to deal with those clumsy keyboard controllers. If you're interested in learning more about basic programming or the keyboard controllers, I have some videos I made a while ago that you can review at your leisure. But if you're interested in learning how I got this keyboard to work with basic programming and my Atari 2600, stick around. We'll go through some schematics, we'll take a look at the little microcontroller I programmed, and also take a look at its source code. So let's begin with an overview of the schematic of the controller we need to emulate. This is a schematic of the Atari 2600 keyboard controller, and it basically implements what's known as a keyboard matrix. The keyboard matrix works by scanning pins 1, 2, 3, and 4 continuously until a button is pressed. And when that button is pressed, one of the output pins, 5, 6, or 9, will become active because the circuit is completed between the scanning pins 1, 2, 3, or 4 and the output pin 5, 6, or 9. And at that precise moment, the Atari 2600 can deduce which of the buttons was pressed because it knows which scanning pin was active at the time and which output pin is active as well. So the goal of this project is to replace the human pressing of one of these 12 buttons with a microcontroller output. The microcontroller is going to respond to some keyboard events, and those keyboard events are going to get translated into what the Atari is expecting. So what we can do is replace each of the 12 push buttons with an AND gate, and then hook up the microcontroller to one end of the AND gate, which is denoted by the blue dot on each of the gates, and then the other connections would follow as shown in the diagram. And so when the Atari scans through the rows, then the gate will only become active when the microcontroller sends a signal, and that will only happen when someone presses a key on the proper keyboard that we're interfacing with this circuit. And in doing so, the Atari 2600 is no wiser that a computer is driving its inputs through the joystick port. So there's one small problem with this approach, and that is that we're going to need 24 available output pins on whatever microcontroller we choose. And for some of the small microcontrollers that are available, like the Raspberry Pi Pico or the Arduino Nano, you don't have 24 output pins available to you. So we'll need to do something a little bit more clever. And that can be addressed by introducing a decoder into the circuit that we're going to build. The decoder lets you take any set of output lines that you want to address and represent them with a binary number. So in this example, we have 8 output lines on a 3 to 8 decoder, and the 3 represents the number of input lines that you need to uniquely select one of those 8 outputs. It's a binary number. In this case, I've used the number 3011 to select D3 as the output. The E pin represents the value that you want to set on that output that's selected. So in our case, we have 24 AND gates we need to uniquely select, We can accomplish that with one 3 to 8 decoder and one 4 to 16 decoder, because 16 plus 8 is 24. So one 3 to 8 decoder and one 4 to 16 decoder will only use 3 plus 4 input pins for selection, which is 7, compared to the 24 that we needed otherwise. And of course, we need the 1 pin for the data value to set. So a total of 8 pins are needed. Now this solution is fine. There aren't really any serious problems with it, but the one issue that I have is that it uses a lot of components and it doesn't leverage some of the firmware features that the microcontroller offers. One approach I'd like to investigate is to eliminate all the gates and to hook up all the 4 scanning pins and the 3 output pins directly to the microcontroller and let it manage the state of the system. So in this configuration, the microcontroller will know the states of pins 1, 2, 3, and 4, and it will also know the state of what the user is doing, pressing on the external keyboard. So when a button press comes in from the keyboard, then the microcontroller can deduce which of the 3 output pins it needs to activate. And that's the approach I want to investigate for this project, because a software solution will be much easier than obtaining a bunch of ICs and wiring them together on a breadboard, etc., etc. Finally, let's not forget that we need to reserve some pins on our microcontroller so that we can hook up an external keyboard to it. Now, whether that's a USB or PS2 keyboard, we're only going to need 2 pins. For the USB, that's going to be a data plus or data minus signal, and for the PS2, that's going to be a clock or data signal. The remaining 2 pins are for power, and those can be hooked up to whatever power source is powering our new device. Alright, so with the theory out of the way, we can now take a look at some of these components which I'm going to use on this project. The most important thing to have is one of these little guys, and you might recognize it as an Arduino Nano microcontroller. More correctly, it's an Atmega 328P clone or an implementation of the Arduino Nano specification, but it's pretty much the same thing. So the reason why I want to use this is because it is dirt cheap, inexpensive. You can get them for about $3 on various online sources from China. And it's quite powerful. It's got a 16 megahertz processor, and it's got plenty of memory for what we need to do. Now, there's only one downside to using this thing, and the downside is that it will not operate as a USB host. That means I cannot stick USB devices into its USB port and have this CPU detect what that USB device is and interact with it. Now, you can plug this into a computer, but it's because this is acting as a USB client. It's getting power off of the USB port, and it's allowing serial communications. But it's not a USB host. So I cannot take my USB keyboard and plug it in here and hope that it gets detected. And that's why I have this keyboard over here, which you'll recognize as a PS2 style keyboard. The PS2 protocol is substantially simpler than the USB protocol, so it makes using a keyboard like this ideal for an inexpensive microcontroller like this. Now, to hook up this keyboard with this microcontroller, I'll need to access the 4 pins that are used on the PS2 protocol. And to do that, I'm going to build this tiny little adapter which effectively exposes the pins from the PS2 cable. It's basically one of these passive adapters that takes a PS2 input and outputs USB, and then I have a little shoddy little cable here that basically breaks out the USB from this female port into 4 wires that I can hook up over here. It's a little messy, I know. I've already ordered the proper cables that will hook up to this, but they're not here yet. By the time this video is finished, they might show up, in which case I'll just retrofit everything to make it look tidy. And one note on these converters, these are passive converters, which means that there are no electronics in here to convert from USB to PS2 or vice versa. It is merely a rewiring or a one-to-one mapping from the pins on here to here. No different than me soldering some wires onto various pins and hooking them up to the appropriate, one of the appropriate 4 pins on the USB side. Next up is I have a pin header. This is an angled pin header, and I'm not using the standard straight ones, which you might be familiar with, only because when I install these pin headers into this microcontroller, they need to fit in this box. And the straight pin headers, the ones that go straight up, will not fit nicely in this box. It's a little too shallow, and I'm trying to keep this as compact as possible. That leads me to these DuPont cables, I am going to cut the female end off and splice them with these two DB9 cables that I have so that I can hook things up and remove them as neatly and tidily and as nicely as possible from the microcontroller once the angled pin header is soldered on there. That leads me to these two Frankenstein clunky looking DB9 cables. I guess that's a good way to describe them. And they look like this because these are just spare parts that I have lying around. In fact, if you've watched some of my other videos where I make controllers, you'll recognize these components. They're basically the ends of an extension cable that I cut off, and I didn't throw it out because I thought I might use it. The other end is what I'm using on the actual controller that I'm working with. So to reuse this, I need to make this male end a female end, and so I bought a pair of these female to female gender changers. So they usually look like that. And I've taken it apart because I want it to mount flush with this thing. You'll recognize this style of project box from some of the other projects I have on my channel. And I had this lying around, so there was no sense in buying the one that I usually use, which is a little bit bigger. But of course, that constrains me to some other of my choices for components over here. Finally, we have some cable glands, which of course will be used to secure these cables to this project box. And then we have these guys, which I have avoided talking about until now. I'll show these in a little bit more detail in a moment, but effectively what I have are two hats or shields or daughter boards. I don't know what the best terminology is for this, but effectively this, when it's hooked up with this 2-pin female to male connector, implements a power bus, which I can stick on my Arduino Nano like so. And now I have 3 vertical pins that implement ground and positive 5-volt bus that I can hook things into. And it just makes interfacing in this box, all the components that are going to need power, a little bit more easier. And this guy here is another hat or shield or daughter board that will fit right over top of the CPU in this configuration. And it implements the 2 resistors that are needed for each of the cables that go to the Atari 2600. I'll talk a little bit about what this specifically does in a moment, specifically with the Atari 2600 input ports. And this is the power source that goes here. So let's take a look at these 2 things in a little bit more detail. And I'll show the construction and their diagrams and schematics. This picture shows my T-shaped power bus mini circuit. On one side, I have an angled 2-pin header, and on the other side, I have a 6-pin header or a 2x3. Each of those columns in the 2x3 is going to represent the positive and negative rail for the power bus. The angled pin header is connected from one side of the circuit board to the bus on the other side via a wire that I'm slotting through the circuit board, and I'm using a double-sided circuit board to make the soldering a bit easier. And this picture shows some pins connected to a wire and some resistors, as shown in the schematic of the keyboard controller on the right side of the page. Now you have to remember that there are 2 keyboard controllers that we have to emulate, and they each have this arrangement of resistors, so we effectively need to duplicate what's shown in the schematic. Now the angled pin headers are connected to the straight pin headers via the leg of the resistor, and it's kind of slotting through both sides of the circuit board and then connected via a solder bridge. All of the 4 resistors meet into the center of the circuit board, which I've bridged all together and connected to this red wire, which is going to be providing power. If you look on the schematic, both of the resistors on each controller hook up to pin 7, and pin 7 is used to provide 5 volts to whatever's inside the joystick or controller's casing. So in this case, we only need 1 wire to go to all 4 of the resistors, and then we can hook up that wire to my power bus to get its power source. Okay, so let's get some holes drilled into this project box, and then we'll start wiring up and soldering these components, put this thing together, and give it a go. Alright, so all this hardware is assembled, so all we got to do is hook it up to the microcontroller and we can start writing some firmware. I've even got a proper PS2 jack. This is a mini DIN 6, and I've soldered some DuPont cable to the other end so that I can also hook this up to the pin headers. But unfortunately, I've made some pretty bad decisions in this design, which I feel the need to disclose right now before we go any further in this project. First, I failed to notice that after applying the heat shrink tubing to both of these cables and their wires, that the diameter of the cable significantly increases to the point where it will barely fit through this large hole of the cable gland. In fact, I was able to get it through, but only barely, and that means that there's no way I'm going to get the cable through the smaller end of the part of the cable gland that actually does the strain relief. So I was thinking, why not just get a larger cable gland? Well, if you look on the box, the holes that I drilled out for the cable glands are pretty much on the threshold of what this box will take for a particular size hole. If I drilled this as a larger hole to support a larger cable gland, it will most likely crack the top of the box over here, or even run into the floor of the box, which you can see is pretty close to the bottom, right over there. So that's out of the question. I'll need both a larger box and a larger cable glands, and I figured there's no point in investigating that or trying to solve that problem for this project. I can just hook these things up and just do without it for the time being. Let's move to the topic of connections and pin assignments now, and also talk about my second mistake, which deals with this resistor network shield. So what I failed to do when I designed this was to actually probe the output pins 6, 9, and 5 to see what's going on there before I actually hooked anything up. And if I had paid attention to the schematic, and if I had paid attention to what the probing would have shown me, that would have been that pins 5, 6, and 9 are constantly held high. You can see on the schematic that pin 6 is pulled up to 5 volts all the time. Pin 6 is usually used for the fire button on the joysticks, and that makes total sense from a pull-up standpoint. Pins 5 and 9 are the analog ports for paddles, and those typically work by having a capacitor that gets charged, and the CPU measures how long it takes to charge that capacitor, and therefore it knows the analog voltage that's being calibrated to that input. So because pins 5 and 9 also have to be pulled up, they have these resistors in line that get fed directly from pin 7, and pin 7 is the power source on all the joystick ports for Atari and Commodore computers. You can also see that on the schematic. Now the reason why there's a resistor there, you don't need to have it. You can hook up the 5 volts directly, but if something goes wrong with your power supply, let's say the voltage regulator shorts out, that total surge of current is going to go straight through this wire, straight through this pin in the absence of a resistor, and directly into the chip that's servicing this and blow it up. So these resistors are put there strategically to limit the current. Unfortunately, I've put these in the wrong place. If I wanted to limit the current to the to the output pins 6 and 9, I should put them after the microcontroller's output between the cable and the microcontroller. So in a future revision of this, I'll probably pull this shield out, put the resistors in the right place, and get rid of this 5 volt voltage source, as it's really not needed in the current setup. Finally, the pins have been selected so that cables can sit on the left and right side without there being any wires crossing over, but there's also a strategic selection in case I want to use interrupts for driving this firmware in the future. We're not going to talk about interrupts too much in this demo because I haven't worked out the software completely, but interrupts operate on a specific port, and a port has several pins assigned to it, and it just so happens that the pins I selected all belong to the same port, so it makes the interrupt implementation a little bit easier. That is for internal or pin change interrupts. External interrupts are these two pins over here, 3 and 2, and we need one of these pins to be reserved for the PS2 signal, which comes from the keyboard. The clock signal of the PS2 protocol is required to go on D3, which is one of the 2 external interrupt pins, and that requirement is imposed by the library I'll be using for processing the signals that come from the keyboard. And this is what the microcontroller looks like with all of its wires connected to it. The power for this will come from pin 7 of one of the 2 joystick ports. In this case, I picked the right one as it's more convenient, And as you recall, pin 7 goes directly to the voltage regulator's output. Now the voltage regulator that's in the Atari 2600 will provide, I believe, 1 amp. I have the datasheet linked to the description below in case anyone wants to verify that. And in any case, that 1 amp is more than enough current to power this device and any cartridge that's running. Don't worry too much about the pin mapping for now. That is the mapping from the wires to the pins on the joystick port and to the pins on the microcontroller. I'll have a document linked to my GitHub page which shows the pin mappings that I've allocated for this particular project in this particular configuration. So with that said, let's now review the firmware for this project. So this is the first source file I want to look at because it kind of provides the foundation for everything that we're trying to do. We need to map certain pins on the joystick ports to certain pins on the Arduino. And we also need to do the same thing for the PS2 keyboard. So this file provides the mapping between those pins and it produces constants for those values. We can see here these are the 2 pins that are required for the PS2 protocol, and below that we have several pins that are mapped to the joystick ports and the Arduino digital pins. The next mapping that's required is the one between the keyboard keys and the pins that are actuated when those keyboard keys are pressed. And that's implemented in this file. For this demo, I thought basic programming would be the ideal cartridge since it has dozens of inputs, all of which are unique, and that will provide a wide variability of the keys that we can use on a PS2 keyboard. Each of the records in this mapping has 3 required components. The first component is the key code that represents the key as it is transmitted across the PS2 protocol. These constants come directly from the PS2 key advanced library, so there's no need to figure out how these operate internally. The second component we need is the color that is assigned to that key. Now, as you recall, basic programming's keyboard controller only has 12 buttons on it, and each of those buttons represents 4 possible inputs into the system. The output selection is basically determined by the color mode that you are operating in. There are 4 colors: white, red, blue, and green, and you can switch between them to get a different mapping of operations on your keyboard controller. So to emulate that, we need to assign a color to each of the keys that we are producing in this mapping. In the case of the F1 key, I've assigned this to the status button, and the status button is assigned the color of white on the basic programming overlay. Similarly, if we were to map the plus operator has a red color on the basic programming overlay. Finally, the third piece of information that's required for a proper mapping is the pair of pins that get actuated when the key is pressed. In the case of the status button or the F1 key, this corresponds to the left joystick port. The scanning pin 1 has to be active, and as a consequence of that, the output pin 5 has to be active. You can review this source file for the complete mapping, or you can take a look at this diagram which shows all the different inputs on the overlay, their pins, and their mapped keyboard keys. Next, we have a pair of classes that utilize this mapping. They respond to the key presses that come in from the user, and they actuate the pins on the microcontroller. That's the Atari keyboard class, and the method that we're interested in is in the write method. Once it receives the key code from the caller, it looks up the mapping records that we just described, and once it locates that, it passes that record to a function that knows how to turn pins on and off on the microcontroller. The lookup function uses a binary search for efficiency, but also because the standard library is not available to the Arduino environment, so we can't use things like hashmap or associative arrays. Here's the second class that can utilize the key mapping, and it's pretty much the same as the one we just looked at, except this one knows how to deal with colored keys. The write method still locates the mapping using the key value that's given to it from the environment, except before the key is written to the microcontroller, we have to ensure that the color is set correctly in the Atari basic programming cartridge. The ensure color operation cycles through the colors, sending the color change operation to basic programming until we get to the desired one. Finally, let's take a look at the piece of code that's responsible for changing the state of output pins. As you'll recall, when you press a button on the Atari keyboard controller, that effectively completes a circuit between a scanning pin and an output pin. So what this code needs to do is effectively recreate the signal that would otherwise pass through from the scanning pin into the output pin. And that's accomplished by these 4 lines of code. We wait for the scanning pin to go high, and then we immediately set the output pin to go high. And then when the scanning pin goes low again, we immediately set the output pin low. And we have to remember that once we're done processing, we have to restore the output pin back to its high state. Now the above code sits in a loop, and I found through some trial and error that the minimum number of times that one of these high-low cycles needs to be repeated is 2 times. And I suspect this is because the basic programming cartridge implements some debouncing logic when a button is pressed, and therefore you need at least 2 cycles, otherwise the button event is completely discarded. Finally, there are probably a bunch of viewers right now staring at this piece of code and saying, "Oh my goodness, I can't believe you've written such garbage." And you're absolutely right. This function effectively implements what's called a busy wait, where the CPU constantly checks a piece of memory for a state change. And that's not a very efficient thing to do. In general, you want the environment to tell the CPU when that memory has changed, and therefore the CPU can sit idle or perform other tasks while we're waiting for that event to happen. In this case, the CPU is actively checking for something which rarely changes on the scale of the computer's clock. Yes, I know this isn't very exemplary code, but what I've done is I've encapsulated this in a policy class with the intention of replacing the whole thing in the future. Ideally, we'll want to use interrupts to notify the code of when something has changed, in this case, when a scanning pin changes state, and then we can respond to it accordingly. That implementation is not ready. It will be released in a future revision, and it will make better use of the microcontroller's resources. Finally, we can put this all together in the code's entry point. Here are the 2 keyboard objects that get defined in the global space. Then we initialize them in the setup routine, and then we start calling things in the main event loop. Effectively, whenever there's a key pressed on the PS2 keyboard, if the key is valid, we forward it to the Atari keyboard, which ultimately figures out which pins are actuated on the microcontroller. And that's about it. I've skipped over a lot of the glue or infrastructure code that keeps this together. If you're interested in seeing the entire source code, I'll have it posted to my GitHub page, which is linked in the description below. Now let's get this code uploaded to the Arduino, and let's start writing some basic programs with a proper keyboard and see what happens. Okay, this program that I'm going to enter has a variation of keywords that are going to cause the cursor color to cycle. And it's a pretty short program, just 3 lines, so bear with me while I type it out. And that's it. So this program basically takes an input from the second keyboard controller, which we conveniently don't have available, and it translates that to a note. So as I entered the program, you notice that the color changed automatically, which is fantastic because that means we don't have to worry about it when entering keys. So let's give it a go. I'm going to increase the speed of playback so that this won't take too long when cycling through, and it will respond a little bit better. And then I'll push F10 to start running the program. There we go. And now I don't have a second keypad, but what I'm going to do is I will use the old cheat sheet here to try and emulate that second keypad by pressing keys that would otherwise have been on it. So any of these should work. 1, 2, 3, 4, 5, all the way to HOR2 Virtual 0. The JKL, MNN, MNO key should work as well. Let's just start playing around with a bit of this and see what happens. So we'll start with, let's say, let's do this over here. Let's start with 1, 2, and 3. 1, note is 0, 2, note is 1. This is good. 3, that's good. And let's try the letter N. That also works. And let's do spacebar. What does that do? Nothing. Oh, that's right, because spacebar is one of those keys that's mapped to a non-playing note. I remember that now. How about Y? Okay. And let's do U. Good. So that wasn't so bad, but it requires knowledge of how the keypads used to work in absence of this keyboard. A way to make that better is to map that second keypad input directly to something like this number pad because it kind of has that same coordinate or alignment of the buttons. And we can make it work specifically just for that second keypad by not sending a color whenever one of these buttons is pressed. I'm not going to do that now, but I'll submit it as a code revision to the sources that I upload to GitHub, and you can review it at your leisure. Next, I'll show two problems that come up in this implementation and a way to mitigate them. The first one happens when I type too fast. Watch what happens when I try and type this sentence as quickly as possible. The quick brown fox, jumps over the lazy dog. Okay, so apart from the spelling mistakes that I had when I tried to type fox, you can see that a lot of the letters have been dropped. Specifically in the word brown and lazy, there's an H over there, that might have been a misspelling. But the reason why these letters are dropped is because of the time it takes to send the letter from this device to the Arduino into the cartridge. You'll remember that in the Arduino, I have an 8-cycle delay or repetition of how long it takes for a signal to get sent into the cartridge. And that was intentional so we can see the color changes happening as I, manipulate the keys. But that's not practical in real life. So we could reduce that, and that will make this a lot better. But an ideal solution is to use a queue and to use interrupts. Whenever I type one of these letters, I want to push it immediately to a queue and not process it right away. When the interrupt fires, then that interrupt will process whatever is on the queue and just push it along as needed. And that should be an ideal situation for this device. As long as I'm not typing exclusively when those interrupts are firing, I should be okay. And in practice, that's probably going to be never. The next problem occurs with the select key on the Atari 2600. This key will reset the state of the program and data in the basic programming memory. So when I type something out, like let's say this shoddy program called Hello Program, you will notice that the cursor is blue, but when I press select, everything gets restored, but the cursor gets changed to white. Now, the Arduino that's tracking the key presses and the color change states does not know when the select key gets pressed. It has no way to receive that information. So it still thinks that the color is blue. Now watch what happens when I start typing. I'm going to enter some numbers, 1, 2, 3, 4, 5. And if I start doing some other operations like assignment, there's this one, and then the plus key, and maybe the minus key. The Arduino has completely lost track of the color that is active, and so we need a way to reset that. I can shut the power off, but that's not very friendly because I'm going to lose whatever has been entered into the program. So what I've done is I've programmed the tab key to cycle through the colors in a way that doesn't send the color change operation into the Arduino. So in essence, it's not tracking this state change. We just have to remember the color that we were supposed to be in and then change it using this button. So I was trying to enter numbers and operate with the arithmetic and assignment operations. Those are all on the red color. So if I change it to red, as I just did, if I start resuming entering letters now, A, B, C, we're back in order. Let's try the arithmetic operations, plus, minus, assignment, everything is good. So because we don't have a hookup into the select key being pressed and getting that notification in the Arduino, we really have no good way to eliminate the tab key from the keyboard. Kind of have to have it around as a fallback or a safety in case something gets out of sync. I guess you could have a color changing LED on the case, and that way you'll know the state of what the Arduino is expecting or the state that it's in, and you can compare that with what's on the screen. But maybe that's a bit of overkill. I suppose we could probably do without that. All right, so that's going to wrap this up for this project, at least this phase of this project. I am planning on making some improvements, as I've alluded to throughout this presentation, so stay tuned for that video when it comes out. And stay tuned for a quick follow-up video that I'm going to make. It's going to include a bunch of things that I couldn't include in this video, specifically oddities that I've discovered with this cartridge while testing, oscilloscope waveforms on what happens when you press buttons on the keyboard controllers, and some other things as well. So thank you for watching. I hope you found this information useful. Hope to see you back soon.